For about 50 years, physics has been wrestling with a truly terrifying question. What happens to stuff that falls into a black hole? I mean, really happens. Does the universe have a cosmic delete button? Well, it turns out the answer is no, and the reason why has less to do with destruction and everything to do with the actual geometry of reality itself.
Okay, to get a feel for this, imagine you toss your diary into a bonfire. It really feels like all those secrets are gone forever, right? But they're not. The information is just scrambled. It's been transformed into smoke and ash and heat. Now, if you had a ridiculously powerful supercomputer, you could theoretically track every single particle and put it all back together. But a black hole? Whoa, that feels like a whole different game. Once that diary crosses the event horizon, it's like it's been completely erased from the universe. And that one simple idea, that information can be lost, threatens to break everything we know about physics.
You see, here's why. One of the absolute pillars of modern physics, quantum mechanics, has this unbreakable law called unitarity. Just think of it as the ultimate no-delete rule for the cosmos. It says, without any exceptions, that information can be shuffled, scrambled, or changed, but it can never, ever be truly lost.
And right there, that's the conflict. Because the other pillar of physics, Einstein's general relativity, is just as certain about its own rule. A black hole's gravity is so powerful that once you cross that line, the event horizon, there is no coming back. Nothing gets out. Not light, not matter, and certainly not the information they contain.
So you've got these two titans of physics, quantum mechanics and general relativity, basically locked in a staring contest. Quantum mechanics is yelling, information is forever, and general relativity is yelling back, black holes erase it completely. One of them had to be wrong. And for half a century, this wasn't just some fun little puzzle. It was a genuine crisis that suggested our entire understanding of the universe was built on a lie. Then, in 1974, in comes the legendary Stephen Hawking. Everyone was hoping he'd be the one to finally sort this mess out. He decided to apply the weird, fuzzy rules of the quantum world to the razor-sharp edge of a black hole. And what he found? Oh boy. It didn't solve the paradox. It took this confusing problem and turned it into an absolute nightmare. So Hawking figured out that because of all these quirky quantum effects popping in and out of existence at the event horizon, black holes aren't perfectly black. They actually glow, just a little bit. They're constantly leaking this faint stream of particles we now call Hawking radiation. And here's the kicker. This means that over almost infinite amounts of time, black holes can completely evaporate and just disappear.
Now that should be great news, right? If the black hole disappears, the information must have gotten out in that radiation. Problem solved. Nope. Here's the catastrophe. Hawking's math was crystal clear. The radiation was thermal. That's just a fancy way of saying it's completely random. It's just meaningless static. It tells you nothing about the diary, or the star, or the astronaut that fell in. All the unique information is just gone.
So think about it. The black hole is gone. The radiation it left behind is just featureless noise. The information is truly, completely vanished. For a while, even Hawking himself thought this just meant quantum mechanics was wrong. The paradox was now deeper and way more terrifying than ever before. To get out of this dead end, physicists had to do something really radical. The big breakthrough didn't come from staring harder at black holes. It came from asking a much deeper, and honestly, a much weirder question. It was a leap that would completely change how we think about reality itself.
What if the whole problem wasn't where does the information go? What if the real issue was that we didn't even have a clue what information is in the first place? And this is the question that just blew the doors off everything. Instead of thinking about information like words on a page, what if we started thinking about it as a shape, as a structure? What if information was just geometry? Okay, so the old way of thinking treats information like it's a physical thing, right? Like a book or a computer file, something you can hold or copy or lose. But this new view, it redefines the whole thing. Information isn't stuff. It's the geometric relationship between all the possible states of a system. It's a structure that can bend and stretch and transform, but it can't be deleted.
And this really gets to the core of it. I want you to imagine a gigantic map of every possible state the universe could be in. A state of pure nothingness is right at the center, at point zero. The more information, or entropy, a system has, the further away it is from that center point. In this new picture, the information is that distance. It's literally a geometric property.
So how does this radical new idea actually solve the paradox? Well, by thinking of information as geometry, we can finally see how it gets out of the black hole.
And it doesn't just blast its way out. It escapes through a process that is so much stranger and so much more elegant.
It all unfolds in 4 pretty mind-bending steps. 1. Particles of Hawking radiation get quantumly entangled with stuff inside the black hole, which creates a geometric link between the inside and the outside. 2. We use this tool called the page curve to track that link, and it gives us hard proof that information is getting out. 3. We find that these weird regions deep inside the black hole, called islands, are actually, geometrically speaking, part of the radiation that's way outside. And 4, the craziest part of all, we realize that wormholes and quantum entanglement are just 2 different ways of describing the exact same thing.
So the page curve. This is the smoking gun. Think of it like a graph that's tracking how random the Hawking radiation is. Now, for the first half of the black hole's life, the line on the graph goes up and up and up, just like Hawking predicted. It looks like total chaos. It looks like the information is gone for good. But then, right at the halfway point of the black hole's life, the curve does something that should be impossible. It turns around, and it starts going down. That's it. That's the moment. That's the mathematical proof that the radiation isn't random anymore. It's carrying the information out.
But how? How is it getting out? Okay, this is where it gets really strange. The concept is called islands. It turns out the math for that downward sloping curve only works if you include a chunk of the black hole's interior, this island, in your calculations of the radiation that's now millions of miles away. It's basically saying that the inside and the outside are no longer separate. Geometrically, they're part of the same system.
And let me be clear, this isn't just some clever math trick to get the right answer on a test. This is a massive clue. This is the universe telling us one of its deepest secrets, that the connections between things might be even more real, more fundamental than the empty space that seems to separate them.
And the whole incredible idea is summed up in one of the most beautiful and powerful equations in all of physics, ER equals EPR.
So what on earth does that mean? Okay, ER stands for Einstein-Rosen bridge. That's a wormhole, a literal tunnel through the geometry of space-time. EPR stands for Einstein-Podolsky-Rosen correlation. That's quantum entanglement, that spooky action at a distance. This equation says they are the exact same thing. A geometric connection is a quantum connection. So how does the information escape? The entanglement between the radiation outside and the island inside is a tiny wormhole. The connection is the geometry.
So just let that sink in for a second. The black hole information paradox. It was a ghost. It haunted physics for 50 years, but it was never really there. It only existed because our definition of information was too simple. We thought of it as stuff that could get trapped. But it was never about things getting lost. It was always about our own misunderstanding of reality.
So to wrap this all up, what have we really learned? We've learned that information isn't a thing. It's the geometric shape of possibility. We've learned that quantum entanglement is the physical thread that pulls that information out. We now know that black holes aren't cosmic shredders. They're cosmic transformers. They just change the geometry of information. And maybe most profound of all, the unbreakable law that information can't be destroyed is just another way of saying that geometry itself is conserved.
And that leaves us with one final, absolutely mind-bending question to chew on. If the solution to one of the biggest paradoxes in history is that information is geometry, then what does that say about everything else? Could it be that underneath it all, underneath space, time, matter, and energy, the very fabric of our reality is nothing more and nothing less than pure information?